So let's do one more exercise, the matrix representation for identity. I think this should be hopefully pretty fast. And so just show that the identity operator has a matrix representation of 1 on the diagonal and 0 everywhere else. In other words, the identity operator, which just, A applied to B just gives you the V vector back. Show that it has a matrix representation that looks, something like this, right? 0, 1. Where there's this diagonal term that's going to be all ones, right? Something like that. And 0 everywhere else. So 1 on the diagonal, 0 everywhere else. And so let's just start with, we have an operator, a linear operator from V into V. And we know that A acting on any vector in this space, including this space VI, is going to equal VI, right? We can rewrite this. We can rewrite this as A applied to vector VI equals, 1 times 1 times VI plus 0 times VJ, where I is not equal to J. Right, so in this vector space V, there are, all these basis vectors, V1, V2, V3, V4, V5, whatever. But when I apply A to V1, I only get V1 and I don't get any of the others. If I apply A to V2, I only get V2 and none of the others. If I apply A to V3, I only get V3 and none of the others. That's all that is saying. And so there's a notation for this here. 1 everywhere, and then 0 when I is not equal to J. So 1 when I equals J and 0 when I is not equal to J. And that is this. So delta ij is equal to 1 when I equals J and 0 when I does not equal J. And this delta Dirac, this Dirac delta function, I think is what it's called. Kronecker delta function, maybe. So it equals 1 when I equals J and equals 0 when I is not equal to J. And so we can rewrite this sum here. So AVI equals the sum over J. The sum over J of ij Vj. And this will return the same thing, right? So if I equals J, then Vj is just Vi. If I does not equal J, then this whole thing is 0, so it doesn't contribute. So I can just rewrite it as this. And what's nice about this is if I have my V1, so V1 presumably is going to look 1 0 0 0. My V2 will look like 0 1 0 0. My V3 will look like 0 0 1 0. And so on, right? So you can see this 1 is just changing positions. And since a matrix is really just joining these vectors together, right? Then what I could say here is that when I do this, I'm going to have an operator that acts like this. A equals 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, and so on, right? So, you know, even if it goes on forever and ever and ever, it's still going to operate in this function. It'll have a 1 down the diagonal and 0 everywhere else. That is a matrix representation for the identity operator. So the identity matrix